The electrical neutral is a critical conductor within an electrical system responsible for carrying current back to the source. It's often misunderstood, but its function is essential for the proper operation and safety of electrical circuits. To understand the neutral, we must first consider a basic alternating current, or AC, circuit. In a typical 120 volts AC circuit, you have a hot wire, which carries the electrical potential from the source, such as a power company's transformer, to the load, like a light bulb or appliance. The neutral wire provides the return path for the current to complete the circuit. Without this return path, the circuit would be open, and the load would not receive any power. The neutral is typically at or near 0 volts potential relative to ground. This is achieved by grounding the neutral conductor at the service entrance, where electricity enters the building. Grounding ensures that the neutral remains close to ground potential, providing a safe reference point for the electrical system. This grounding is crucial for preventing voltage buildup in the neutral, which could pose a shock hazard. The neutral is not the same as the ground wire, although they are interconnected to the service entrance. The ground wire is primarily a safety conductor. It provides a path for fault current to flow back to the source in the event of a short circuit or ground fault. This allows the overcurrent protection device, such as a circuit breaker or fuse, to trip and interrupt the circuit, preventing electrical shock and fire hazards. The neutral, on the other hand, is intended to carry current under normal operating conditions. It's part of the regular circuit pathway, while the ground wire only carries current during fault conditions. One common misconception is that the neutral wire is not carrying any current. In a balanced circuit, where the current flowing through the hot wire is equal to the current flowing through the neutral wire, this might seem true. However, the neutral is still carrying current, and it's essential to size the neutral conductor appropriately to handle the expected load. In multi-wire branch circuits, the neutral conductor can carry significant current, especially when the loads on different phases are unbalanced. For example, in a 240 volt split-phase system commonly found in residential homes, two 120 volts hot wires share common neutral. If one hot wire is carrying 10 amps and the other is carrying 5 amps, the neutral will carry the difference, which is 5 amps. If the neutral is undersized, it can overheat and potentially cause a fire. It's also important to understand the consequences of a broken or disconnected neutral. If the neutral connection is lost, the voltage on different parts of the circuit can become unbalanced. Some loads may receive a higher voltage than they are designed for, while others may receive a lower voltage. This can damage equipment and create a safety hazard. For example, in a 240 volt split-phase system with a lost neutral, one 120 volt circuit might see 180 volts, while another sees only 60 volts. This voltage imbalance can quickly destroy sensitive electronic devices. Because the neutral is normally at or near ground potential, it is sometimes mistaken as being safe to touch. However, this is a dangerous misconception. The neutral carries current, and if there is a break in the neutral conductor or a high resistance connection, the voltage on the neutral can rise significantly. This can create a shock hazard, especially if someone touches the neutral and ground simultaneously. Electrical codes, such as the National Electrical Code, or NEC, provide specific requirements for the sizing and installation of neutral conductors. These requirements are designed to ensure the safety and reliability of electrical systems. For example, the NEC specifies the minimum size of the neutral conductor based on the expected load. It also requires that the neutral be grounded at the service entrance and that the grounding connection be properly sized and installed. One important aspect of neutral conductor sizing is the concept of neutral current reduction. In some cases, the NEC allows the neutral conductor to be smaller than the hot conductors based on the type of load being served. For example, if the load consists primarily of nonlinear loads such as electronic ballast or variable frequency drives, the neutral conductor may need to be oversized to handle the harmonic currents that these loads produce. Harmonic currents are multiples of the fundamental frequency, which is 60 Hz in the United States. These currents can cause the neutral conductor to overheat and can also interfere with the operation of sensitive electronic equipment. When working with electrical systems, it is crucial to follow all safety precautions and to consult with a qualified electrician if you have any questions or concerns. Always to energize the circuit before working on any electrical components. Use a voltage tester to verify that the circuit is de-energized before touching any wires. Wear appropriate personal protective equipment, such as insulated gloves and safety glasses. Never work on electrical systems when you are wet or standing in water. The electrical neutral plays a vital role in the safe and efficient operation of electrical systems. Understanding its function, importance, and safety considerations is essential for anyone working with electricity. Proper installation, sizing, and maintenance of the neutral conductor are crucial for preventing electrical shock, fire hazards, and equipment damage. The neutral conductor is also important to consider in the context of electrical panels. Inside an electrical panel, the neutral wires are typically connected to a neutral busbar. This busbar is a conductive strip that provides a common connection point for all the neutral wires in the panel. The neutral busbar is also connected to the grounding electrode conductor, which runs to the grounding electrode system, such as a ground rod or metal water pipe. This connection ensures that the neutral is properly grounded and that any fault current can safely flow back to the source. When wiring an electrical panel, it is important to make sure that all neutral wires are securely connected to the neutral busbar. Loose connections can cause arcing, overheating, and voltage drops, which can lead to equipment damage and safety hazards. It is also important to keep the neutral busbar clean and free of corrosion. Corrosion can increase the resistance of the connection, which can also lead to overheating and voltage drops. In addition to the neutral busbar, electrical panels also have a separate ground busbar. The ground busbar is connected to the grounding electrode conductor, and it provides a connection point for all the ground wires in the panel. The ground wires are connected to the metal enclosures of electrical equipment, such as appliances and lighting fixtures. If there is a fault in the equipment, the ground wire provides a path for the fault current to flow back to the source, tripping the circuit breaker and preventing electrical shock. It is important to keep the neutral busbar and the ground busbar separate. The neutral busbar should only be connected to the neutral wires, and the ground busbar should only be connected to the ground wires. Connecting the neutral and ground busbars together can create a ground loop, which can cause unwanted current to flow through the grounding system. This can interfere with the operation of sensitive electronic equipment and can also increase the risk of electrical shock. In some cases, the neutral and ground busbars may be bonded together at the service entrance. This is typically done to provide a low impedance path for fault current to flow back to the source. However, it is important to make sure that the bonding connection is properly sized and installed. An undersized bonding connection can overheat and can also reduce the effectiveness of the grounding system. The NEC provides specific requirements for the bonding of neutral and ground busbars. These requirements are designed to ensure the safety and reliability of electrical systems. When working with electrical panels, it is important to follow all safety precautions and to consult with a qualified electrician if you have any questions or concerns. Always to energize the panel before working on any electrical components. Use a voltage tester to verify that the panel is de-energized before touching any wires. Wear appropriate personal protective equipment, such as insulated gloves and safety glasses. Never work on electrical panels when you are wet or standing in water. The electrical neutral is an essential component of electrical systems. Understanding its function, importance, and safety considerations is crucial for anyone working with electricity. Proper installation, sizing, and maintenance of the neutral conductor and the neutral busbar are essential for preventing electrical shock, fire hazards, and equipment damage. In commercial and industrial settings, the role of the neutral conductor becomes even more critical due to the increased complexity and higher loads of electrical systems. Three-phase power systems are commonly used in these environments, and a neutral conductor plays a vital role in ensuring balanced operation and mitigating the effects of unbalanced loads. In a balanced three-phase system, the current in each of the three hot wires is equal in magnitude and 120 degrees out of phase with each other. In this ideal scenario, the neutral conductor would carry little to no current. However, in reality, loads are often imbalanced, meaning that the current drawn by each phase is not equal. This imbalance creates current flow in the neutral conductor, which must be sized appropriately to handle the expected load. The NEC provides guidelines for sizing the neutral conductor in three-phase systems, taking into account the potential for unbalanced loads and the presence of nonlinear loads that generate harmonic currents. Harmonic currents are particularly problematic in three-phase systems because they can cause the neutral conductor to overheat and can also distort the voltage waveform, affecting the performance of sensitive electronic equipment. To mitigate the effects of harmonic currents, it is often necessary to use oversized neutral conductors or to install harmonic filters to reduce the amount of harmonic current flowing through the system. Another important consideration in commercial and industrial settings is the proper grounding of the neutral conductor. The neutral conductor must be grounded at the service entrance to provide a low impedance path for fault current to flow back to the source. This grounding connection must be properly sized and installed to ensure that it can handle the maximum fault current that could occur. In some cases, it may be necessary to use multiple grounding electrodes to provide a more robust grounding system. In addition to grounding at the service entrance, the neutral conductor may also be grounded at other points within the system. This is known as multi-point grounding, and it can help to reduce voltage drops and improve the stability of the system. However, multi-point grounding can also create ground loops, which can cause unwanted current to flow through the grounding system. Therefore, it is important to carefully design and install multi-point grounding systems to avoid these problems. The neutral conductor also plays a critical role in the operation of ground fault protection systems. Ground fault protection is designed to detect and interrupt ground faults, which are faults that occur when current flows from a hot wire to ground. Ground fault protection systems typically use a ground fault sensor to monitor the current flowing in the neutral conductor. If the current in the neutral conductor exceeds a certain threshold, the ground fault sensor will trip a circuit breaker, interrupting the circuit and preventing electrical shock. Ground fault protection is required in many commercial and industrial settings, particularly in areas where there is a high risk of electrical shock, such as wet locations or areas where equipment is used outdoors. When working with electrical systems in commercial and industrial settings, it is essential to follow all safety precautions and to consult with a qualified electrician if you have any questions or concerns. These systems are often more complex and dangerous than residential electrical systems, and it is important to have the knowledge and experience necessary to work on them safely. Always to energize the circuit before working on any electrical components. Use a voltage tester to verify that the circuit is de-energized before touching any wires. Wear appropriate personal protective equipment such as insulated gloves and safety glasses. Never work on electrical systems when you are wet or standing in water. Understanding the role of the electrical neutral in commercial and industrial settings is crucial for ensuring the safe and reliable operation of these systems. Proper installation, sizing, grounding, and maintenance of the neutral conductor are essential for preventing electrical shock, fire hazards, and equipment damage. Furthermore, it's important to delve into specific scenarios and calculations related to neutral conductors. Firstly, consider a single-phase 120-volt circuit powering a resistive load of 10 amps. In this scenario, the hot wire carries 10 amps to the load, and the neutral wire carries 10 amps back to the source. The neutral conductor must be sized to handle at least 10 amps continuously. Secondly, imagine a 240-volt split-phase circuit powering two 120-volt loads. One load draws 5 amps, and the other draws 8 amps. The neutral conductor carries the difference between the two currents, which is 3 amps. The neutral conductor must be sized to handle at least 3 amps continuously. Thirdly, envision a 3-phase 208-volt Y-connected system with balanced loads. Each phase carries 20 amps. Ideally, the neutral conductor carries no current. However, if the loads are unbalanced, the neutral will carry the unbalanced current. If phase A carries 20 amps, phase B carries 18 amps, and phase C carries 22 amps, then neutral carries 4 amps. Fourthly, in a three-phase system with significant nonlinear loads, harmonic currents can significantly increase the neutral current. If the fundamental current in each phase is 15 amps, and the third harmonic current is 5 amps, the neutral conductor can carry up to 15 amps of harmonic current in addition to any unbalanced fundamental current. This requires a larger neutral conductor. Fifthly, consider voltage drop calculations for the neutral conductor. Like any conductor, the neutral conductor experiences voltage drop due to its resistance. If the voltage drop is excessive, it can affect the performance of the loads. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. The voltage drop in the neutral conductor must be considered when calculating the overall voltage drop in the circuit. Sixthly, the NEC Table 310.15. B16 provides ampacity ratings for conductors based on their size and insulation type. This table is used to determine the appropriate size of the neutral conductor based on the expected current. It is important to consider the ambient temperature and any dirting factors that may apply. Seventhly, ground fault circuit interrupters, or GFCIs, are designed to protect against electrical shock by detecting small imbalances in current between the hot and neutral conductors. If the difference exceeds a certain threshold, typically 5 mA, the GFCI will trip, interrupting the circuit. GFCIs are commonly required in wet locations such as bathrooms and kitchens. Eighthly, arc fault circuit interrupters, or RFCIs, are designed to protect against fires caused by arcing faults. RFCIs detect abnormal arcing conditions and trip the circuit breaker. They can help to prevent fires caused by damaged wiring or loose connections. Ninthly, proper torquing of connections is crucial for ensuring the reliability of electrical systems. Loose connections can cause arcing, overheating, and voltage drops. All connections, including those on the neutral busbar, should be torqued to the manufacturer's specifications. Tenthly, regular inspection and maintenance of electrical systems are essential for preventing problems and ensuring safety. This includes checking for loose connections, damaged wiring, and corroded components. The neutral conductor should be inspected as part of the overall inspection process. In conclusion, the electrical neutral is a fundamental component of electrical systems, playing a critical role in completing circuits, carrying current, and ensuring safety. Understanding its function, proper sizing, grounding requirements, and the potential impact of unbalanced and nonlinear loads is essential for anyone working with or designing electrical systems. Adhering to the NEC guidelines and following best practices for installation, maintenance, and safety are crucial for preventing electrical hazards and ensuring the reliable operation of electrical equipment.